My dear students, let me welcome you all to a new edition of physics. In this edition, we'll learn about electrical instruments. The first device is the moving coil galvanometer. We'll learn about its idea, scientific idea, its mode of work, its structure, how to convert it into DC ammeter and DC voltmeter. So let's get started. Electrical instruments, moving coil galvanometer. What about the moving coil galvanometer? It is an apparatus for measuring very weak current intensity. So talking about the use of the device, it is for measuring, very weak current intensity. And what about the idea of the device? What about the scientific idea? It is based on, it is based on the magnetic effect of the electric current. Also, you can say it is based on the magnetic torque. And what about the structure of the device? So talking about the structure of the moving coil galvanometer, okay, we've got a permanent magnet and a coil which hangs in a strong magnetic field produced by, horseshoe magnet. And we've got a pointer that moves on uniform scale, equally spaced scale. Or we can say it is a linear scale. And we've got jeweled bearings, and poles of the magnet are curved. And the coil is wound around soft iron cylinder. And we've got hair springs. Okay, this was about the structure of the device. And what about its mode of work? So talking about mode of work of the moving coil galvanometer. When the current required to be measured flows in the coil, the vertical sides of the coil experience a couple. They experience electromagnetic couple. Okay, the coil rotates till the couple is balanced by the opposite couple, the mechanical couple produced by the hair springs. So the coil rotates till the couple is balanced by the opposite couple, the mechanical couple produced by the hair springs. And what about the function of the soft iron core? Okay, talking about the function, first function is it concentrates the magnetic flux lines. Okay, so the core concentrates the magnetic flux lines because soft iron has high permeability. The soft iron core, together with the curved poles of the magnet, produce radial magnetic flux. And this is very important. This is a crucial factor, that leads in uniformity of the scale. The soft iron core, together with the curved poles of the magnet, produce radial magnetic flux. And now we want to know the function of the hair springs, hair coils. Okay, as I said, they produce an opposite couple opposite to the electromagnetic couple to balance it. So once again, they produce an opposite couple which balances the electromagnetic couple. They bring the coil and the pointer back to rest position when cutting the flow of the current required to be measured. After finishing measuring the current, they lead the current in and out of the coil. Yes, this was about the function of the hair spring. And now we've got something very important. We call it sensitivity of the galvanometer. Sensitivity is denoted by letter S. What about the sensitivity of the galvanometer? Definition of sensitivity, it is the scale deflection. It is the scale deflection per unit current intensity flowing in the coil of the galvanometer. By the way, unit current intensity here is 1 micro, ampere. So once again, it is the scale deflection per unit current intensity flowing in the coil of the galvanometer. So sensitivity is equal to theta over I. Theta indicates the deflection, scale deflection per unit current intensity. And how to increase the sensitivity of the device? How to increase sensitivity of the galvanometer? Okay. First of all, the coil of the galvanometer should have a large area. So increasing the face area of the coil. The coil of the galvanometer should have a large area. This is one factor. Another factor that increases sensitivity, the coil should have a large number of turns. Large number of turns. The permanent magnet should be strong. Hairsprings should be, weak. And what about the jeweled bearings? Yes, they should be very smooth. In this way, we can increase sensitivity of the device. It means increasing the sensitivity means enable the device to measure very weak current intensity. And now, how to convert the galvanometer into DC ammeter? The question is why you want to convert it into DC ammeter. As a matter of fact, to measure high current intensity. Moving coil galvanometer is designed to measure very weak current intensity. What if we want to measure high current intensity? We'll convert it into DC ammeter. DC ammeter means direct current ammeter. What about the direct current ammeter? It is a moving coil galvanometer whose coil is connected in parallel to a very low resistance called shunt. So the ammeter is a galvanometer, but we need a small resistance to be connected in parallel to the coil of the galvanometer. Once again, this ammeter is a moving coil galvanometer whose coil is connected in parallel to a very low resistance called shunt. In front of you, we've got the galvanometer and a small low resistance connected, in parallel to the galvanometer. Resistance of the galvanometer, is Rg. Resistance of the shunt, Rs. The maximum current that the ammeter can measure is denoted by capital I. Full scale deflection of the galvanometer is Ig. Current that passes through the shunt is Is. So once again, Rs is the resistance of the shunt. Is is the current passing through the shunt. Actually, most of the current, most of I, passes through the shunt because it is, low resistance. Ig is the full scale deflection of the galvanometer. They are connected in parallel. Okay, so the potential difference across the galvanometer is the same as that across the shunt. So we can say, saying anything, let us discuss the function of the shunt. What about the function of the shunt? It extends the range of the device. What does it mean? It extends the range of the device. Yes, it enables the device to measure higher current intensity. it decreases the total resistance of the device. The shunt draws most of the current required to be measured. The shunt draws most of the current required to be measured, such that a small fraction of the current passes through the galvanometer, the coil of the galvanometer, and the galvanometer is not damaged. And now, how to determine the value of the shunt? Determination of the value of the shunt. Okay, the shunt is connected in parallel to the galvanometer, so the potential difference is the same. Potential difference across the galvanometer is the same, yes, as that across the shunt. Voltage across the galvanometer is equal to the voltage across the shunt. So we can say IGRG, the voltage, product of I and resistance, is equal to ISRS. So the value of the shunt denoted by RS is equal to IGRG over IS. So we can say, yes, of course, the current entering the parallel combination, the maximum current measured by the ammeter is denoted by I, and of course it is equal to IG plus IS. Okay, so we can say IS is equal to I minus IG. In this way, the value of the shunt will be equal to, yes, IGRG over I minus IG. Okay, once again, RS indicates the value of the shunt. IG is the full scale deflection of the galvanometer. RG is the resistance of the galvanometer. I is the maximum current that the ammeter can read. And IG, as I said, is the full scale deflection of the galvanometer. And what about sensitivity of the ammeter? What about sensitivity of the ammeter? Okay, it is the ratio between IG and I. IG, full scale deflection of the galvanometer. I, maximum current that the ammeter can read. And how to obtain IG? Yes, it is voltage divided by resistance. So IG is equal to V over RG. Don't ever forget, they are connected in parallel. So we've got the same voltage. And what about the total current? Current I. The maximum current measured by the ammeter equals V over R total. R total is the, yes, equivalent resistance of two resistances, RG and RS, connected in parallel. So it is the product over the sum. V, of course, will be crossed out. So we can say IG over I is equal to R total over RG. So the ratio between IG to I is equal to RGRS over, yes, RG between two brackets, RG plus RS. RG will be crossed out, so the ratio will be RS over RG plus RS. Okay. And now talking about the direct current voltmeter. DC voltmeter. What about the direct current voltmeter? Yes, a DC voltmeter coil galvanometer, whose coil is connected in series to a very high resistance called the multiplier. So once again, the coil of the galvanometer is connected to a high resistance in series. Okay, you remember when converting the galvanometer into, yes, an ammeter, we used a low resistance, and this resistance is connected in parallel to the coil. But now we'll use high resistance called multiplier, and it will be connected in series to the coil of the galvanometer. So once again, DC voltmeter is a moving coil galvanometer whose coil is connected in series to a very high resistance called the multiplier. Galvanometer, yes, resistance of the galvanometer is Rg, high resistance connected in series to it. This resistance is called multiplier and it is denoted by Rm. And the full scale deflection of the galvanometer is denoted by Ig. Since they are connected in series, the same current passes through them, which is Ig. Potential across the multiplier Vm, and that across the galvanometer Vg. And what about the voltage that the voltmeter can read? It is V. And of course, it is the sum of Vm plus Vg. So V is the voltage that the device can read. And now, what about the function of the multiplier? What about the function of the multiplier? First of all, it extends the range of the device. It increases the range of the device. It increases the total resistance also of the device. So, first of all, it extends the range of the device. What does it mean? It enables the device to measure higher potential differences. Also, it increases the total resistance of the device. And now we want to determine the value of the multiplier used. Okay, Vm is the potential across the multiplier, Vg is the potential difference across the galvanometer, V is the potential across the whole device. It is the voltage measured by the voltmeter. Okay, Vg is equal to IgRg, Vm equals, IgRm, and the voltage measured by the device, denoted by capital V, equals Vm plus Vg, or Vg plus Vm. So it is equal to IgRg plus IgRm. We want Rm, we want the value of the multiplier. What about the value of the multiplier? Okay, V minus IgRg equals IgRm. So the value of the multiplier Rm equals V minus IgRg over Ig. This is the law to be used, okay, for calculating the value of the multiplier. And now talking about sensitivity of the voltmeter. What about it? So talking about the sensitivity of the voltmeter. Sensitivity of the voltmeter, it is the ratio between Vg to the total voltage. The voltage read by the galvanometer to that read by the voltmeter. And voltage is the product of current and resistance. So Vg equals IgRg. Total voltage equals Ig between two brackets Rg plus Rm. So we can say the ratio between Vg to V is Rg over Rg plus Rm, as Ig is crossed out. We've got some questions. Give reason for. The ammeter must have low resistance. The ammeter must have low resistance. Okay, if the ammeter had a high resistance, the total resistance of the circuit to which the ammeter is connected increases in a way that would appreciably change the current. Okay. Second, give reason. The voltmeter must have high resistance. The voltmeter should have high resistance. Why? If the resistance of the voltmeter was low, A large fraction of the current flowing in the circuit would flow through the voltmeter, and the current flowing in the circuit is appreciably changed. Okay. And now we've got a problem. A galvanometer of the resistance 10 ohms, so Rg is given to be equal to 10 ohms, gives its full scale deflection. Full scale deflection is Ig, gives its full scale deflection when a current of 500 microampere passes through its coil. This is Ig. 500 micro should be converted into ampere, multiplied by, yes, thank you very much, 10 to the power of negative 6. So the device gives its full scale deflection when a current of 500 microampere passes through its coil. Explain how to convert it into an ammeter that reads up to 1 ampere. 1 ampere is I. The maximum current read by the ammeter is I, so I equals 1 ampere. How to convert it into, yes, a voltmeter that reads up to 10 volt. 10 volt is V. Okay. So once again, given in the problem, the resistance of the galvanometer is equal to 10 ohms. Ig full scale deflection 500 micro, so 500 times 10 power negative 6 ampere. Current required to be measured, maximum current is 1 ampere. We'll use, yes, the expression, the relation of the shunt. Okay, Rs is equal to Rg over I minus Ig. So it is equal to 500 times 10 to the power of negative 6 times 10 over 1 minus 500 times 10 to the power of negative 6. Value of the shunt is equal to 0.005 ohm. So we have to add something very important here. We should mention the way the resistance should be connected to the coil of the galvanometer. So a resistance of 0.005 ohm is connected in parallel to the coil of the galvanometer. Okay, second part of the problem, we wanted to measure, yes, voltage. Okay, so we want to convert it into a voltmeter. We'll use, yes, the formula of the multiplier. Multiplier is equal to V minus Ig Rg over Ig. Maximum voltage required to be measured is equal to 10 minus 500 times 10 power negative 6 over 10. Ig equals, yes, 1 minus 500 times 10 power negative 6. So the value of the multiplier is equal to 19,990 ohm. So a resistance of 19,990 ohm should be connected in series to the coil of the galvanometer. Value of the required resistor, required shunt resistor to decrease the sensitivity of an ammeter of resistance 24 ohm to its 1/4, 1/4. Okay. What is the value of the total resistance of the ammeter and the shunt? Resistance of the galvanometer equals 24. We want to reduce sensitivity to 1/4. This means that, yes, I equals 4 Ig. Ratio between Ig to I equals 1/4. So I equals 4 Ig. Value of the shunt is given from the expression Ig Rg over I minus Ig. So Ig, okay, times resistance of the galvanometer 24, I equals 4 Ig, so 4 Ig minus Ig. So we can say 24 Ig over 3 Ig. Ig will be crossed out. In this way, we've managed to obtain the value of the shunt. And what about the resistance of the ammeter, the device produced? It is a galvanometer and a shunt resistance connected in parallel. So resistance of the emitter is obtained from product over the sum, 24 times 8 over 24 plus 8, it is 6 ohm. And this way we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you.